Hello, this is Chuck Ridgway, Automation Technology Manager at Horner. Thanks for joining us for another Tuesday live stream. Here's our topic for today, and it's hands-on PID tuning on the Horner OCS. Now, today's topic was suggested by P.J. McAllen, who actually suggested two topics. He suggested sequential stepper moves, which we covered a few weeks ago, and today's topic. Now, specifically, what PJ wanted to know was, how do I tune a PID loop when the output of the loop is a digital variable instead of an analog one, or a digital signal instead of an analog one? I thought that was a great idea for a topic, and so we're covering it today. Now, for you automation engineers out there, or those just learning about automation, you probably fit into a couple different groups, one of a couple different groups when it comes to PID. For those of you with a lot of experience, you're probably very comfortable with PID. PID is an integral part of the systems you work on regularly, and for you, tuning a PID loop is probably like falling out of bed. No big deal. But there's another camp out there that just isn't as comfortable. They don't have the level of experience. Maybe they learned about it in school, or maybe they've read about it in books, or maybe they've even watched our webinar on PID that we put on a few months ago at Horner. But in either case, they don't have enough real-world experience to really be comfortable with the PID tuning process. So that's the group we'll probably be able to help the most today in today's session. Okay, let's take a look at how we're going to break down today's session. Whoops, I'm going to have to go way back to the beginning here. I'm all the way at the end. So meanwhile, I'm going to go ahead and talk about another topic, and that is the fact that doing a live PID demonstration, which will definitely be part of what we accomplish today, is something that's not necessarily conducive to live streams. Because what happens with a live stream, obviously, is that when you execute your experiment, if it takes a really long time to go through, then that doesn't make for the most compelling watching. So here's what we decided to do. Instead of doing it purely live, I spent last week doing a whole series of PID tuning experiments until I hit upon an experiment that I was relatively happy with for the purposes of demonstration. So I was able to set up a process, perform an auto tune, make manual adjustments, and be relatively happy with the results in about 40 minutes or so. But even 40 minutes is an awfully long time to do an experiment online live. So here's what we did. I enlisted Marcy Tyree, our marketing guru, to take my 40 minutes of footage and to really compress that down to about 17 minutes or so. And as she did so, she put a real-time clock on the screen so that no matter where we are in the video, even when we're fast-forwarding through the boring parts, we can always see the elapsed time through the process. We think that's pretty important, and we think the demo is a pretty good one. So anyway, hopefully we'll bring that to you in a few minutes and you'll get some good value out of that. All right, now let's go to the content. Okay, here's how we're breaking down today's topic. Okay, we're going to do a quick review of PID control and the Horner PID instruction. Now, we covered these in great detail in the PID webinar we put on a while back that's available on YouTube and also on our website, of course. But we're going to break some new ground today with some of the details we provide you on some PID tuning methods. We're also going to answer PJ's question about what are the implications of using a digital output to control a process versus an analog one. And of course, we're going to have that PID tuning demonstration that I just talked about. So let's go ahead and dive right in. So PID is a mathematical approach to process control. So on the screen there, you see a couple of equations for the traditional form of PID and the ISA form of PID, and there's others as well, but those are the two that we've implemented at Horner. And one thing that's important to keep in mind is that understanding your process is way more important than understanding all the details of the math. So really what you need to take out of this is just that there's three elements to the PID algorithm: proportional, integral, and derivative, and each of those offers something different when it comes to controlling your process, and we'll talk about that more as we move along. Okay, let's get started with the process itself. Process control is the automated control of a process. Makes sense, right? And there's some terms that we need to become familiar with. First, the process variable. That's the variable that's being measured or controlled in the process. So for a pizza oven, for instance, it's the temperature of the oven. Next, let's move on to the control variable. That's the variable we're going to manipulate that will cause the process variable to change. So in our pizza oven example, maybe it's a gas valve that's controlling the flow of gas to a burner, which is ultimately going to control the temperature of the oven. Okay, so that's the control variable. As we continue to kind of build out our diagram here, next we're going to talk about the set point. That's the desired value for the process variable. So in our pizza oven, if we want to make pizza at 600 degrees Fahrenheit, then our set point could be 600 degrees, for instance. Next, the error term. What is the error term? Well, that's the difference between the desired value of the process variable and its actual value at any given time. So if we're wanting to make pizza at 600 and that's our set point, and we're currently at 400, well, we've got an error term or an error of 200 degrees. Finally, what is a controller? In this diagram, the controller effectively is the equipment that's tasked with controlling the process. So if you're talking about an application being controlled by a Horner OCS, the Horner OCS is the controller here. Okay, now there are several goals for a controller when you're talking about PID control or process control in general. You want to get to the set point fast, you want to get all the way to the set point, and you don't want to overshoot too much. So those are all goals for the controller. Now luckily, we have proportional, integral, and derivative available to help us in that effort. So the proportional is going to help us get there fast, the integral is going to make sure we get all the way there, and the derivative is useful when we want to make sure we don't overshoot too much and to make sure we're as stable as we need to be. So the whole goal of PID from a tuning standpoint is going to be all about selecting the coefficients that will help us balance the proportional, the integral, and the derivative to control our process the way we need to. Okay, next let's pivot to discussions on the Seascape PID instruction. As I mentioned earlier, we have two variations of the instruction available, both an independent version and its ISA version. Okay, it's based on integer-based math, so don't panic. You don't have to have floating point capability to do an excellent job of doing PID control. Also, our PID instruction requires that you allocate 16 registers or an array of 16 variables to it as additional resources. And the algorithm does support auto-tuning using a modified version of Ziegler-Nichols open loop method, and we'll talk about that in a little more detail as well. And on the output side, the PID instruction can be used to control either digital or analog values. Again, getting back to PJ's question for today. All right, now when you drop a PID instruction in your logic and you go to configure it, obviously you've got a main configuration dialog box where you're going to configure a whole variety of different parameters. I'm not going to go into terrific detail on these. We'll go into some detail on our demonstration today, and then of course there's additional detail in the PID webinar. But the bottom line is this is where you configure where's my set point coming from, what's my process variable, what's my control variable, etc. Also, one other note, when you use a PID instruction in your logic, you almost always are going to leave it on all the time. So even in those occasions where you want to manually control the output, you're not going to take power away from the instruction. What you're going to do instead is you're going to put it into manual mode through the use of a manual variable that's been assigned to the block. And then you can temporarily manually control the output, and then when you're ready to go back into automatic, you can put it into automatic again. So almost always, you're going to have an always-on contact in front of your PID instruction. Okay, now there's also auto-tune parameters to configure, mainly just a bit that triggers the auto-tune process and another bit that you monitor that says that it's done. Okay, so if you're not using auto-tune, then you don't need to worry about these parameters. If you want to use auto-tune, they need to be configured as well. Now getting back to those 16 words that need to be allocated to the instruction. The chart on the right there shows all the detail on what's included in those 16 words. And again, we'll go into detail on some of those parameters today during the demonstration portion of things, and there's additional detail available in our PID webinar. Now one of those words, partway down, says config word, and the additional details on the config word are shown here. So it's a bit-mapped word of about 12 or 13 bits to help you do some of the configuration of some bit-type parameters. Now let's talk about the specifics or the implications when you're wanting to use a digital output to control a process. Now first of all, Why would you use a digital output to control a process? Well, let's talk about an example. Again, getting back to our pizza oven. Let's say we have a gas pizza oven. So in this scenario, obviously we're going to want to control the temperature of the oven. And with a gas oven, we're going to vary the amount of gas that's being provided to the burner in order to impact the temperature of the oven. Now, to do that, we're going to adjust a proportional gas valve, which can be adjusted from 0 to 100%. So that's definitely an analog actuator that we'll be adjusting in the case of a gas pizza oven. But let's take a look at the example where we have an electric pizza oven, specifically an electric pizza oven where we're using on-off control to actually regulate the heat. So in that scenario, in order to add heat to the system, we're basically going to be turning an electric heating element on and off. And so the control of that heating element is a digital signal. So the implications of that from a programming and a setup standpoint are as follows. First of all, you're going to start out by setting up your PID loop as you normally would, but then you're going to make some adjustments at the end for a digital output type process. First, you need to add an output coil to your PID instruction. On the screen there, I have one called heater SSR. Okay, and that wouldn't be there, again, if I had a gas-controlled oven or that I was controlling. So you need to add that for a digital output process. And then you need to tell the PID instruction that it's being used with a digital output. So to do that, getting back to that config word I talked about on a couple slides ago, bit 15 of the config word needs to be set to tell the algorithm that, hey, we're using digital output control. Next, we need to consider the output cycle time. Now, if you're using a completely solid-state output actuator and you have no concerns whatsoever about any kind of mechanical wear or damage over time because of cycling very frequently of your output, then you don't need to worry about that. You can leave it at 0. But if you do have an actuator where you don't want to have an excessive number of cycles and you would like the time between cycles to be greater than 0, then you can set that cycle time in number of seconds using that parameter. And then finally, you must set the upper clamp to 32,000 and the lower clamp to minus 32,000 if you're going to be using a digital output to control the process. Okay, now at runtime, what's going to happen? Well, the OCS PID loop is still going to calculate a number or an integer value for the CV, for the control variable. But it's going to turn the output on if that control variable value is 0 or above. If it's negative, it's going to turn that variable off, okay, or turn the output off. All right, so that's what's going to happen at runtime. All right, next let's talk about different PID tuning methods. And again, the whole idea of PID tuning is to select the coefficients that are going to allow the right amount of proportional, integral, and derivative control in the algorithm to adapt to your process. So the first method we're going to talk about is manual tuning, or sometimes called the experimental approach. And this is a completely valid approach and one that is used on some processes because it's the only one that actually will work properly. So how does manual tuning typically go? Well, you start out with zeroing out the coefficients for P, I, and D, and then just plugging in a value for your proportional term. Okay, and then you're going to execute that value for proportional only control as the first experiment. Now, you can either just plug a value in, or you can try and calculate a value to plug in for that. Now, if you decide to calculate the value, you can take advantage of the fact that the control value equals the proportional coefficient times the error term. So you can take advantage of that equation. So let me give you an example. So let's say in our pizza oven that as we're heating up the pizza oven, we want that heater to be on full go up until we get within, let's say, about 5 degrees Celsius or so of the set point. We can take advantage of that CV and KP equation, and we can determine that, okay, full go on our control variable is 32,000 counts. And if 5 degrees Celsius is scaled in our application, let's say to 500 counts, then once we have them both scaled to counts, we can do the math and come up with an initial KP of 64. So that would be a good starting point that may represent what we're trying to do. Now, once you've plugged in some sort of term, whether you've calculated or you're just plugging it in off the top, you need to let that run and you need to find out if it's going to work for you. And of course, you're going to need to increase it if things are taking too long to get to the set point. You'll need to decrease it if you're overshooting way too much. But anyway, at some point, you'll have dialed in relatively well your KP term. And next is time to add in a little bit of integral. And typically, you don't need a very big value. And generally, what the integral is going to do for you is it's going to help you get all the way to the set point. So if you're kind of getting stuck above the set point or below the set point, for instance, by a delta there, then you may want to add an integral to kind of help with that situation. Once you're happy with your integral, and of course you're doing experimentation all the way through here, once you're happy with your proportional and your integral, then you can add some derivative in to help improve your overshoot and improve your settling time. Okay, so that's the manual tuning or experimental type approach. Now you can also take a mathematical type approach, okay? And that is you could take advantage of something called the Ziegler-Nichols Tuning experiment. And this is something that's been developed since the 40s, and it's being used by a lot of people today because it works relatively well in a lot of particular processes. Now, I'm not going to go into all the detail that you see on the screen there, but the bottom line is this. You're going to go through a tuning experiment, or basically let the process run with a certain procedure. And then while that's happening, you're going to be recording some values really for the purpose of determining some time constants, or at least some time values. And then once you've determined those time values, then at the end, you're just going to plug those into the equations on the lower right to come up with your initial coefficients for P, I, and D. Okay, so that's the Ziegler-Nichols tuning experiment. We've got a little more extra detail, at least from the theoretical side of things, in our PID webinar that are available to you. All right, now some of you are saying, well, wait a minute, what I want to do is auto-tune my system. That's what I want to do. Well, keep in mind that auto-tuning is not basically a substitute for understanding your process, okay? Having a good understanding of your process. But you can use auto-tuning in a variety of different processes. And of course, as I've already mentioned, it is supported by the Horner PID algorithm. So here's the process that's used for auto-tuning with our PID algorithm. Basically, it's a modified version of Ziegler-Nichols. We start by the control engineer, the one who is actually kind of monitoring the tune. The control engineer is going to plug in an appropriate set point value for the experiment. So in our pizza oven, maybe 600 is the set point we want to use, okay? Now, then they're going to kick off the auto-tune process. The first thing that's going to happen is the OCS is going to set the CV at maximum, all right? And that should drive things up towards the set point. As soon as it exceeds the set point, that control variable is going to be driven to minimum, or minus 32,000. That's going to cause it to drop below the set point. When it gets below the set point, then kind of one cycle is complete. The OCS is going to continue that process for 3 complete cycles, and based on those experiments, it's going to calculate the P, the I, and the D coefficients. So that's effectively the approach being used by the OCS, a modified version of Ziegler-Nichols. Okay, now we get to the demonstration for our PID tuning. And this, again, is about 17 minutes long or so, and I think there's a lot of good information in here, and I hope you'll get a lot of good out of it. Okay, let's kick this off. Okay, here's my test setup for our little PID tuning experiment. I have a vessel here, or a bowl, basically with half of a liter of water in it. I'm going to heat the water. That's going to be my process. I have an immersion heater here, just a low power 300 watt, pretty safe unit here. I've got an RTD probe that's measuring the temperature of the water. My XL4 is my controller here. I'll be executing the PID on the XL4. We are going to be using a on-off control, or a digital output from the PID loop that is going to run through a solid state relay that is controlling the heater. Okay, so that is our physical setup. Let's head to Seascape and take a look at how we have it set up here. Okay, here's my PID. I'm using the auto-tune option as well as the ISA option. All right, have everything configured using variable base advanced ladder. Let's go take a look at our auto-tune settings. All right, I've assigned a start bit and a done bit, a couple of Boolean variables for the auto tune function. I'm going to go ahead and tune all three elements, P, I, and D. From a controller response standpoint, I'm going medium. From a noise filtering standpoint, I'm going with the minimum. And that's because I'm not concerned about electrical noise causing my process variable, which in my case is my temperature, to bounce around a lot. I don't think that's going to happen in my case, so I don't need a bunch of noise rejection or noise filtering. I'm going to tune at the full set point, not 2/3 of a set point. I might check that if I was concerned that, you know, a big overshoot at my full set point could cause a problem for my machine while I'm tuning. So I'm just going to, but I'm not concerned about that. Okay. Now let's go take a look at the tuning page. So here's what I have set up on the tuning page, or at least a reflection of the tuning page. Don't have any of the coefficients set yet for P, I, and D. The auto tuning is going to give me a starting point for that. My sample period is 100 milliseconds. No bias has been configured. I don't have any deadband, upper or lower, configured. You'd set a deadband if you didn't want your CV to be hunting around a lot near the set point. In my case, I have a solid state relay controlling a heater. I have no concerns about any kind of mechanical wear out or mechanical life shortening of my devices that are controlling my process. So therefore, I'm not concerned about a few extra cycles on the solid state relay, so I'm not going to set deadband in this case. Upper clamp 32,000, lower clamp minus 32,000. Those have to be set that way if you're using a digital output to control a PID loop. Okay, I'm leaving error term, slew time, output polarity, and derivative all default, and I have enabled PWM, which is basically indicating I'm using a digital output to control my process. And I'm setting the cycle time at 0 because, again, I'm not concerned about cycles that happen frequently on my solid state relay. No issues there. Now, even though the output is a on or an off, I'm still, the OCS PID loop is still doing an integer-based CV calculation. Now, if the value of the CV happens to be below 0, then my output will be off. My digital output will be off. If the CV calculation results in a 0 or higher, then my output will be on. So that's what will be happening. Okay. During the tune, we can monitor what's happening on these bar graphs. In my case, my process variable and set point are scaled to the point where they're not going to get above about 8,000. So I'm going to narrow in my range there to make it more meaningful. All right, and I think I'm ready to start my tune. So let me switch over to my lab setup here. All right, I'm in manual mode. You can certainly tune from manual mode. That's not a problem. My heater's enabled. I'm going to go ahead and set my set point for tuning at 60 Celsius. Currently, my water before heating is at 17 or 18 degrees Celsius. Let's go to my tuning screen. And I should be able just to kick off the tune here. There we go. You'll notice my SSR is on. So what we're going to be executing here, or what we are executing here, is a Ziegler-Nichols tuning experiment being automatically run by the OCS. So what's happening here is the OCS will run the process to the set point and actually a few degrees above the set point. And then it will drop it back down below the set point, actually a few degrees below the set point, and it will do that 3 times. Okay, and during that time, it's calculating some values, it's monitoring some values, it's doing some timing calculations, and at the end of those 3 cycles, it will come up with a suggested or a set of coefficients for P, I, and D. All right, and then we can take those and test them and see how they do. All right, so that's where we're headed. Now, as you can see, the temperature has started to move now. It takes a little bit of time, of course, for the heating to actually start to the point where we can measure the temperature, but now the temperature is moving. So I'm going to go ahead and let that run, and while it does, I think I'm going to go ahead and try and put our tuning screen on display here. So let me see if I can turn that on. Okay, now let's switch from our tuning window to a chart. Now during auto tuning, you have to get above the set point by a little bit before it actually turns off. So you can see in this case, after 0.3 degrees C, based on the scaling, we turned off the SSR. And so even though the temperature continues to creep up because of inertia, we are now headed down on the first cycle. So we're going to need to go below the set point by a similar amount that we went above it before this cycle will be complete. Okay, you probably noticed that the solid state relay turned back on again once we got below the set point by a few tenths of a degree. So we're now actually on the second cycle of the auto tune experiment. Okay, this is our last cycle and we're on our way down. As soon as we get below the set point by 2 or 3 tenths, the auto tune should be complete. And it is. You can see the done bit come on. Now as soon as I turn off the start auto tune button, you'll see the done bit goes off as well. Okay, all right, so that's auto tuning. Okay, now that we're done auto tuning, I need to close this window and reopen it again, and then I can see my suggested tuning parameters. Okay, or actually these are the ones that are now in place. All right, so the next step is always to test these because there's no guarantee they're going to work at all, frankly, although they usually do work pretty well. There's also no guarantee that you can't improve them through a little bit of manual tweaking. So the first thing we need to do, though, is we need to actually test these and see how well they work. Now we're still in manual mode, so I'm just going to hop right into automatic mode and we'll see what happens. Okay, so I'm going to leave my tuning screen. Okay, and I'm going to switch into automatic mode. Now these parameters that were just calculated are being put to the test, and we'll see how those go. Now one thing that I'm keeping my eye on here is that we're actually getting further away from the set point. So that's obviously a concern, and if it continues, then my thought would be that we may have a scenario where the integral term is creating problems. That's not unusual in some applications. So as you can see, we are definitely headed the wrong direction. Let's head back to Seascape and take a look at things here. I am looking here at the CV calculation, and again, as long as it's negative, the output is off. Okay? So every once in a while, it'll pop on for a short period of time. But we're continuing to get further and further away from our set point, continuing to drop. Okay, so what I'm going to do now is I'm going to clear out, back in Seascape, I'm going to clear out this integral term. All right, by typing a 0 and hitting update controller. And immediately my output turned on. Okay, my CV calculation went to maximum immediately. So that kind of gives me a pretty good clue that it was my integral term that was causing problems with my output, or at least preventing it from staying on long enough to get closer to the set point. Okay, let's head back to the bench and take a look, and hopefully we can see after we overcome the inertia of the water, we hopefully will be able to see the temperature climbing up instead of down. Yep, there we go. So you can see the solid state relay is on longer, and you can see that we are now headed the right direction in terms of temperature. All right, let's watch this and see how we do as we approach the set point. Okay, we're approaching the set point from below, and it'll be interesting to see what kind of overshoot we get. So it looks like 6 or 7 tenths of a degree was our overshoot on this first time through here. Now let's see what it looks like on the bottom side of the set point. Okay, so about 0.75 probably. I saw one little bit of 0.8 below the set point there. So it looks like we're within about, at this stage at least, we're within about 1.5 degrees Celsius. Pretty well centered around the set point. We'll watch it for a while and see how it does. Okay, the next thing I'm going to try and do is I'm going to see if increasing our derivative term is going to make a difference. And to really see if that makes a difference or not, I'm just going to go ahead and double it. All right, so I'm going to take it from its current value all the way up to, let's say 90. All right, basically doubling it. And I will hit Update Controller, and we'll see what kind of impact that has. It doesn't appear to be helping. If anything, it probably appears to be taking it the other direction. So I'm going to let it go up through this cycle, and then I'm going to try reducing it by half. So it was at 45 originally. I doubled it to 90. Next, I'll try dropping that down to, let's say, 20 to see if that offers an improvement or not. But I'll wait a couple minutes before I do that. Okay, now normally I would let this run a little while longer, really on all these trials, frankly. But for the purposes of demonstration, I think I've come to the conclusion that these changes to the derivative have not really made a difference in the positive direction. So I'm going to go back to the original coefficient value after the auto tune, and I would imagine we'll settle back in at about, plus or minus 0.7 or so. Okay, now one thing I want to have a quick discussion of, and that is the proportional term. I haven't played around with the proportional term at all. If I go through and do a calculation on kind of the different proportional terms I might be interested in using, basically the calculation I came up with was, say, 64 was about the largest proportional term I wanted to use. And that would be because of how close to the set point, for instance, when we're heating water that's just been poured in, how close to the set point do I want to be before I turn the heater from 100% off to some lower level? In other words, from a CV calculation of 100%, how close to the set point do I want to be before that CV calculation drops below 100%? So, and by the calculation I've made, if I have a proportional value of 64, then I'm going to keep that CV calculation at 100% up until 5 degrees before I get there. So basically what I'm saying with this long-winded description is the suggested coefficient of 56.5 is pretty close to 64. So I don't think bumping it up to 64 is going to make much of a difference. It might save a few seconds in heating the water from the beginning, but it might have a negative impact on how tight we are or our overshoot. So I think I'm going to leave things alone. So to summarize, for at least this reasonable tune where I'm plus or minus 0.7, I took the tuning parameters that were suggested or found during the auto tuning, and then after trying them out and seeing that we were unable to use those parameters exactly, I basically zeroed out the integral term because it was pretty obvious that we were in a runaway situation both directions. So by zeroing out the integral term, we got things to plus or minus 0.7, and the other things I've tried so far haven't really improved anything. Okay, so I think as I let this run, it'll probably settle back in again to where we were when we started, and hopefully this was a good demonstration for you. Okay, so I think the most important thing about that video, if nothing else, was it shows you the process that you go through when you are tuning a PID loop. You know, if you're starting with an auto tune, getting through the auto tune, getting to the point where you're making manual adjustments, checking to see how those are doing, and then kind of taking it from there until you're satisfied with the results. Okay, so hopefully you found some value in that. So in our wrap up today, I want to mention that here's kind of the big idea for today. There are a variety of methods you can use for PID tuning, from manual tuning, or sometimes called experimentation. You can take a more mathematical approach with the Ziegler-Nichols open loop experiment. And you can also mix auto tuning in with manual refinement as well. So lots of different ways to tune PID loops. And again, just to reiterate, it's way more important to kind of understand how your process works than it is to know the details of the math. And then getting back to the fact that some processes are controlled with digital actuators, some extra setup is required, and in that mode, whenever your CV calculation is 0 or above, the digital output will be on, and it'll be turned off whenever your CV is negative. So hopefully that was valuable for you today. All right, I want to mention that next week, our session is hands-on with exchanging global CPU tags from a Rockwell Logix CPU with an OCS. So kind of like using an OCS in an HMI type capacity with a Rockwell PLC, although of course the OCS does way more than just operator interface functions. So you could be using this approach and doing data logging or WebMI or a whole variety of different things. But again, that'll be at our normal time, Tuesdays at 2 o'clock Eastern. Also, if you haven't already, don't hesitate to subscribe to our channel. It doesn't cost anything, of course. And if you choose notifications, you'll be notified when we go live, as well as anytime that we post a new video. And we've been posting quite a few videos this year. Okay, so hopefully you got some good out of today's video. I'm looking forward to seeing you all next week. So let's all get out there and do some good.